Very good afternoon to all of you. I hope you can all hear me clearly and see my screen. Let's start with today's work. So far, we have covered three chapters. Now, we are in the, we have covered four chapters. Now, we are in the fifth chapter, which is the chapter on color image processing. And thank you, Ashia. Good afternoon, Manu. We have already taken an introduction to the color image processing in the last class. Today's class we are going to talk further. Specifically, what we are going to look into are color models. Now remember last class we talked about color perception. How do we perceive a particular color? But remember, for mathematical purpose, for representation purpose, particularly for representation in terms of computer algorithms, the perceived colors must be modeled in some digital values, numerical values. So that is what we are going to achieve or understand in this class. We are going to talk about color models. So the three major color models or most important color models are RGB, red, green, blue, as its name suggests, CMY, cyan, magenta, and yellow. An extension to CMY is CMYK. We will talk about that. And the third is HSI, hue, saturation, and intensity, which is sometimes also called as brightness or simply value. It's a gray value. So we are going to talk about these color models in today's class. So the first one is RGB color model. So in the last lecture, we had seen that human eye perceives the different wavelengths differently. An amount to which a particular wavelength is absorbed depends on its value. And we have also seen that there are three distinct peaks in this absorption. So if you do a threadbare analysis, then we have seen that the three peaks, they somewhat come at these three colors, red, green, blue. So we take these three colors as the primary colors and we can add these three to create the other colors. So that way these colors are called additive color identities or additive primaries. So we can now create a model. It's a there are three coordinates. If you have such a model, then there would be three coordinates RGB, which can in fact correspond to three coordinates of a Cartesian coordinate system. So a Cartesian coordinate system is used to explain the RGB color model. How does it look like? So I have a drawing over here. These are my axes. This is origin. This is one axis. This is another axis. This is third axis. So these are our origins and axis. This is called red axis. This is called green axis. This is called blue axis. So what happens if you're on a particular axis? So if you're on a particular axis, it's the red value which whose intensity changes. So if you are towards the origin, for example on our axis, the red will look almost like dark black or dark gray. As you go towards the away from the origin towards this side, the red becomes more and more brighter. At this end towards the corner, the red becomes very bright. Similarly, green, pure green, at this end the green is darker. As you go towards this side, the green becomes brighter. Same applies for the blue. It's darker toward dark gray, but as you go towards this side, it goes towards blue. So these are my primary colors which are represented on three axes. The If you are anywhere at this point, at this corner, then it will have an equal amount of red and blue. An equal amount of red and blue would create a magenta, which is a secondary color. If you are at this plane, BG plane, and at this point, then you have equal amount of blue and green, that is cyan. And if you are here and here, then you have an equal amount of yellow, strong yellow. So these three secondary colors, CMY, cyan, magenta and yellow, are at three other corners of the cube. The diagonal represents the grayscale while the black is at the origin. The black color is at the origin. It is the darkest of on all the three scale and it represents black. White is the opposite corner. So here you get all the three. Here the coordinates will be 1, 1, 1. By the way, in this diagram, it's a normalized diagram. The brightest is taken as 1. So whichever bit, number of bits you may use, suppose if you are using 8-bit color system, then this will be 255, but here it is normalized as 1. So yeah, so that is your grayscale from black to white. So the grayscale lies along the diagonal. Now if you take any other color, possible color, it is going to be inside this cube. So if I'm here, then I can always draw a vector from the origin to that particular point and its coordinates or its components along x-axis, along g-axis, r-axis and blue axis will give me the component of the three colors in that particular value. So all the colors theoretically at least lie inside this cube because one is the maximum bright blue, or one is here maximum bright red, one is here maximum bright green. So all the other colors are encompassed inside this cube. You can always draw a vector as I said. Each vector will have three components. The three components would represent the three component colors as we do in normal vector algebra, x, y, z component. Here is a real system. Remember in the last lecture we had shown a color model, but here is the light of three different torches are thrown on a screen in the dark, in absolute dark, and you will get this kind of thing. This is a simple experiment that you can try to do at home even. Go to the market and buy some gelatin paper. The gelatin papers are available in red color, blue color, green color, orange, lots of colors. Select these three RGB colors and then take three torches and you put in front of them, you put the three gelatin papers, the red on one, the green on the other and the blue on the third one. Once you do that, then your three torches will become RGB torches. I mean, gelatin paper allows only that color to pass through, which color it looks like. So you get three colored torches. Now you can throw those light on a wall in a darkness, complete darkness. Get into a dark room, preferably a white painted wall, and then you throw the colors, throw the light, and you can easily observe these kind of patterns. You can see it clearly here. This is pure red, pure blue, pure green, fully bright, and when they merge into each other, you can see that the blue and red merge to give magenta, the blue and green merge to give you cyan, and these two will merge to give you yellow, and finally all three will merge to give you white. So this is how it looks like even in practice. Additive color RGB color model. Here is the color cube. If you have to actually paint it, it would look like this. Remember, this was corner was red, this corner was green, this corner was blue, this corner was white, this is blue and red mix, magenta, this is red and green mixed, yellow, and this is cyan, which is green and blue mixed. At any given time, you can see three planes of this cube. So this plane, at this corner it is red, this corner it is magenta, this is yellow, and this is white, and it will that's how colors will change. Similarly, on this corner this is cyan, green, yellow, white. Top planes, very simple: blue, magenta, white, and cyan. So you have, these are the three visible planes. Three planes are invisible. If you have to imagine the three invisible planes, they may look like this way, the hidden planes. So you can see that this is R is equal to 0 plane. R is equal to 0 means this side, back side's plane, this one. So this side is blue and this side is green. So you go from blue to green at the bottom. At the top, you will get some brighter value of, I mean, the origin is almost black. So you go from black to green. As you go up, the blue becomes brighter. So brighter blue to cyan. That is what that back side. On this side, sorry, on this side, from at the bottom you'll go from black to red, so black to red, and the top you will go from some light blue to magenta. That's what the transformation here. And there is a bottom plane here which is again not visible. It has black somewhere at the origin and green at this end, so black and green, black and red, and yellow at this corner. So these are the three background planes which are normally not visible if you draw a diagram. Okay, so going ahead from here, I have how to test a color model. So it's very simple. Whatever software you are using, most of the software employs some type of color model. If you're using PowerPoint, if you're using Keynote, if you're using Pages, Word, etc. Almost all these softwares use some type or other type of color model. Most of the softwares actually offer all the types of basic types of color model to experiment with. So I'm going to demonstrate this. Later on, you can check this demonstration using on your own system, using your own software. So I'm using it on Keynote. The equivalent of Keynote, a popular equivalent of Keynote is uh, PowerPoint. So you can do is you can just drag and drop a shape of a square, and then you go to the properties of it and you go to the colors. So whatever fill colors are there. Now you can see that I have a slider here which is call it as RGB slider. So I can put different RGB values in it, and depending on what RGB values I put, I will get my color. So right now this is an 8-bit imaging, remember this. So maximum is 255, 255, 255. There are 256 levels. Remember, just like in grayscale we had levels, now we will have levels in the colors also. So in the previous drawing I showed today was 0 to 1. Now in real software this is scaled to 0 to 255. Starting with the red slider first. This is not red, this is a blue slider, but nevertheless. So you can see that some issue is there. Wait. Okay. Yeah, I mean, this is, at least to me, it does not look like a red slider. So, and this is also not looking like a blue slider. So any which way, there are some, apparently there are some issues over here. So maybe I can skip this demo, but you people can check your system to figure out what is the sliding, what sliders are available, and accordingly you can take your RGB values to fill up your box, and you will get different boxes. There is apparently some issue with color models here, or which I have not understood what kind of system they have used. So any which way, going ahead, I will show you with the other one. CMYK was there. So CMY model, cyan magenta color model. This is another color model which is often used for printing purpose. So remember that, as I said, that on three corners you have RGB, other three corners you have cyan, magenta and yellow, and you can very well put your three axes along these three direction: magenta direction, yellow direction and cyan direction, and you can create another color model out of it. So that is another legitimate color model. These are called secondary colors of light. So if you throw cyan, magenta and yellow, you may not, cyan, magenta and yellow color lights, you may not create all the colors, but these are the primary colors of pigment. So all the painting, not painting, all the printing work that happens through these colors, and for printing it's a primary color. I had shown you the CMY or CMYK printer photographed with the ink tanks attached to it in the last class. So that is an important thing. Color printers, copiers require this. These are subtractive colors in a sense that if you throw white light on a wall which is painted cyan, it will subtract red from the white. So if you remove red from the white light, then the rest of the colors look like cyan. So that is how it is called subtractive color, unlike RGB, which are additive in color. So that is how it works out. So typically, if your RGB values are known, and if you want to know your corresponding CMY values, then you just have to subtract. So for example, C will be equal to 1 minus R. This is what it means. M will be equal to 1 minus G. Y will be equal to 1 minus B, and so on. So this is how things will work. Now, typically for printing, we the dark gray which is created by CMY is not of a very good quality. It is a muddy black or dark gray. Typically doesn't give you the good contrast to the printing. So make the contrast better, the black is added as another pigment. The black pigment is normally represented by K. So for all commercial printing, which is called a four color printing, is nothing but a CMYK printing. So you use these four colors: cyan, magenta, yellow, sorry, and black to print the materials. So most of your books, stationery, anything that you get printed, if you get a photograph printed on an inkjet printer, if you get a banner, chart paper, anything, it all uses this kind of system or model. So let me see if I can demonstrate the CMYK model. At least it was working in CMYK. So I have a CMYK here model. So this is cyan. So I can change. No. To me, this is not red, but this is cyan. So this is how it is changing. No, I don't think even this demonstration is working. So let's go ahead. We'll take up demonstration some other day. The third color model is HSI color model, that is hue, saturation, and intensity. Now, the problem with RGB color model is that, or CMYK color model is that the it's good for printing and it's good for projecting. For example, when the TV screen produces images, it generally uses RGB. All LCD screens, in fact, for that sake. Uh, any projector, if it is projecting image on the screen, it is using an RGB color model. Anything which is being printed uses CMY or CMYK color model. That is the only color model which is needed, which is useful for printing. But the problem with human perception is that we don't see these colors independently. Unlike human ear, human eye is very limited in its strength. For example, if red and blue are mixed together, then human eye cannot see them as red and blue. But human eye only see a magenta. It cannot see red and blue. Unlike human ear, if you play a tabla and the guitar together, human ear can resolve the two data independently. But human eye can't. If you have red and orange mixed together, or red and yellow mixed together, it would look orange. Looking at orange, what we will say, which color is that? So you will say it is orange color. Your eyes cannot see red and yellow independently. So we don't perceive colors as RGB or as CMY. That is not in our capacity. In our capacity, we see colors differently. How do we see colors? So we see colors in terms of hue, saturation, and brightness. Now, what is hue? So hue is a color attribute that describes a pure color. That, for example, this looks like red. When we talk about color, this is red, this is blue, this is purple. So we talk about color as a hue as a pure color. That is our primary attribute to identify color. For example, I am presenting four attributes: the red, yellow, green, and blue. This is a little warmer blue, but that's fine. So I'm presenting you four different colors over here. Now, we can also talk about whether the color is saturated or not. So saturation tells you that how much pure color is there and how much light it is there. So for example, I have two color example I'm presenting here. This is a pure red, almost very strong red. Now there's a pure red is a very subjective term, and I will talk about that also a little later. So this is a very strong red. Now here the red is diluted. Diluted with what? So it's diluted with white, in fact. So it gets little weaker, little pinkish. This is light pink, and this is so light that it almost look like white. Similarly, I have a blue here, which is, I would say, a very strong blue. And again, its intensity drops. So we say medium blue, light blue. So that is another way we differentiate color. Once we identify the hue, we identify the saturation, that how much saturated it is. Then the third attribute that we assign is brightness or intensity. That is another third attribute. We are all familiar. We have described this attribute as gray level earlier, and it is used for even achromatic images. If there are no colors, still brightness plays the role. How much bright or how less bright a particular color is. So this is an example. You can see that this is a very bright red, and as you come here it becomes a dull red, and this is a very dull red. So again, this is the third attribute. For example, in daytime everything looks colorful, go out and see. But if you get into night times, Since light is not there, everything looks dull. Same red color looks very dull on a cloudy day, but very bright on a sunny day. So that is how third way we describe colors. So we don't describe colors. You don't look at the color of a car and say, oh, this has this RGB value. You never say that. You say that, oh, this is a bright red color. Oh, you say it is a dull red color. So we describe color in terms of hue, saturation, and intensity, but not at RGB. So that is why we use this color model, the HSI color model, which is more needed to, which is more tuned to human understanding of color. Also, it becomes very important because it decouples the intensity component from color carrying information. Remember, when you say RGB, then each R value on the axis has intensity data also. So if you go towards the origin, it gets darker. If you go towards the away from the origin, it becomes brighter. So it carries intensity data, but in HSI model, intensity data is separated, and that is why it becomes a very interesting and at times very useful color model. RGB is ideal for color generation. HCV is HSI, it should be, for its description. So how do we design the HSI color model? So very simple, we take the RGB cube and it gives us the first hint how to design. You make the RGB cube stand on one of its vertices like this, appears like a diamond. Okay, shape doesn't matter, as I will come to it in a while. Now if you make it this way, then you know that the topmost portion vertex will become white, bottom vertex is black. You make it stand that way. You know that at the corners, if you go, you get your bright colors. If you recall, this was one value 1 for the red, that is maximum red. This was value 1 for the blue, that is maximum blue. This was the value 1 for the green, that is maximum green. Similarly, this will be brightest yellow and brightest cyan and brightest magenta. That means all around at the periphery, the colors are very bright, highly saturated. The word saturated we will use here. So at the periphery, the colors are very saturated. But remember, as you go up, it is reaching towards white. That means as you go up, the colors should get more, sorry, the pure hues are there at the corners, but as you go up, they become less saturated. As you go down, the intensity drops to black. So you can see that this can be used to design our HSI color model. For example, if you draw a triangle like this, a plane in fact, a triangle which is in a plane here, one side is this diagonal, other side is this, and this side is this, then this point will be almost dark, this end of the triangle almost black, this end of the triangle would be almost white, while this end will be a very bright cyan. Now if you go take this axis, stand at this point and go towards, wait a minute, stand at this point and look at the color. It has some medium value of cyan. Now if you go down, you can see that it has a darker value. If you go further down, it has further darker. If you go up, it becomes lighter. So now if you from here, if you go towards this side, you can see that it becomes more saturated. At the end, you get the strongest possible cyan. So this is a saturated cyan because at the end the value is 1. Here blue is also 1 and green is also 1, 1, 1. So it's the strongest cyan, but as you go towards the center, it gets weaker. Same will apply here also. The cyan is very strong here, of course not maximum, but very strong. As you go towards center, it gets weaker. But this plane would be darker than this one because it is below towards the black side. So you can imagine different planes in this. Each plane will have some intensity, and as you go from center towards periphery, the saturation will increase. But this is only for one color I am discussing, that is cyan. How can you take the same logic to different colors? Straightforward. You draw this triangle in different places. For example, if you draw this triangle here, then you get same thing for yellow. If you draw this triangle for red, you get the same thing for the red. If you draw this triangle for blue, if you will get the same discussion for the blue. So what does it indicate? Can we simplify it further? This looks very complicated drawing. We can simplify it further. One of the basic simplification is that you divide this into multiple planes. Take one plane at a time and understand that. And the shape, actual shape of the diamond does not matter as long as we remember three things. One, as you go up and down in this drawing, you will change the intensity. Number two, as you go from away from the center or towards the center, you will change the saturation. More saturated at the periphery, less saturated towards the center. And third, as you turn the triangle towards other corner, you get different hues. So as long as you remember 3 points, it does not matter whether it's a diamond or a cylinder or a sphere, it hardly matters. Let's take this further. So I have now the diamond has been simplified, as I said, and I have taken one plane. I mean, there are three planes, consider just one plane. So then we have already discussed the pure colors are at the periphery. So the three sides in this triangle, cyan, yellow, red, and three corners, green, blue, red, cyan, yellow, magenta, green, blue, red. All these will be the saturated colors as you are towards the periphery. Colors gets desaturated towards the center. So this point, if it moves towards the center, it gets lighter. If it moves towards the periphery, it becomes brighter. And the position of the plane on the vertical axis gives intensity. So if the triangle is here, then it will be very less intense. If the triangle is here, it's more intense. If it is at the top, it is white. If it is at the bottom, it is dark. This is going to be my triangle at any one point. Say at the middle, this is going to be some shade of gray. These are my pure colors at the periphery. So you can take this a little further. As I said, why to keep it triangular and diamond, etc.? Can we make a more easy shape? Yes, we can. For example, we can make it a circle instead of a triangle and show all those six colors as 6 points: green, yellow, red, magenta, blue, cyan, and you are done. Again, the logic remains the same. The direction represents hue or color. The distance from the center represents how bright or how less bright, how much is the saturation. And the plane in which this circle is drawn will give you the intensity. So consider a circular plane. Pure colors are at periphery, as we had discussed. These are all pure colors. Red is taken as 0. Now we are putting some mathematics. So red can be taken as some 0 of the hue scale. Remember, again there are shades of red and there is a particular red. I'm not getting into that kind of detail. And then angle from the red gives a particular hue. So for example, if this is 0 and if I say my hue is at 180 degrees, so you are at cyan, for example. If you are at 120 degree, you are at a green. If you are 60 degree, you are at yellow, so on and so forth. So this angle will give you the hue, and the length of the vector is the saturation. So if this is my S vector, this length will give me saturation, this angle will give me hue, and position of this plane in that vertical slice which is passing through the center along the axis gives me the intensity. And as I said, the shape doesn't matter. Earlier we had discussed with triangle, you can make even a hexagon or whatever. It does not matter as long as the definition remains the same starting from the red. So how would you convert from RGB to HSI? So straightforward conversion. Now we have understood if the value is, if B is less than or equal to green, it is theta. If B is greater than G, blue is greater than green, then 360 minus theta. That you can cross check with our discussion. Theta value can be determined by using a complicated formula. I would recommend you people to memorize this. Generally, I don't do make this recommendation, but there's no point into getting in the derivation. But then RGB values, once they are known, theta can be calculated. And the S vector's length saturation gives one is given by 1 minus 3 by R plus G plus B into minimum of RGB value, whichever is the minimum. So these are the three conversion. Oh, again, I have a demo. Hope to be lucky this time. Let's see. So this is my RGB, if you all can notice. Here, this circle. So this is the plane selection tool by which I can select the plane in which, intensity plane in which I want to keep my colors. So if I go on this side, then entire plane goes at the highest level, very bright, and center becomes white. If I'm here, then the plane descends on the intensity axis, the center becomes gray, mid gray. If I'm here, then it all descends at the lower axis and everything becomes dark. So this is the way you can select a given plane for the HSI model. Now in this, as I said, as you wrote, this is my pointer. So as you select your pointer, you can change the color. This is the maximum saturated color. Look at the box. Now I'm at yellow. The box has a yellow hue. Now I'm at orange. The box has an orange hue. Now I'm at red. Box has a red hue. So typically, as I said, it starts from 0 at the red, go around, and you can have different hues and color and come back to red. So this is the hue circle that can be obtained. Now for a given hue, this length from the center will give you the saturation. So if you take this towards the center, you will find that it's getting less and less saturated. Finally at the center it becomes some shade of gray. In this case it is white. But I can do the same thing at some other plane, and you can see that the colors hues are now less saturated, and toward the center it turns into gray. So this kind of arrangement is available in most of your computers. You can check. Let me see if this also were HSB. They call it HSB, remember, B for brightness instead of intensity. So I can, again, this is the brightness scale. I can select, let me just select this. Now this is the brightness scale. I can select it, make it white, make it black, or whatever. This is my hue scale. Remember, it says 179 degree, but at white it will not show you anything. So keep it at the center. Saturation keep high. Yeah, so high, 100% saturation, 100% brightness. Now I can select my colors. You can see that 0 degree is for the red hue. As you slide, you can see that the hue is changing in degrees, and it ends at 359. So you made one complete circle. Saturation, you can repeat the same at half saturation. You can see here, and on intensity scale you can again come at the center and you can repeat the same thing. So yeah, that is the demonstration here. So I hope these Today's lecture and today's talk does explain these three models sufficiently detailed. For the next lecture, we are going to look into one or two more technical aspects of color models, and then we can go ahead from the color model idea. We can stop here. Thank you. We will meet at Google Meet for discussion after this. Please come there.